Okay, this is the notes for Unit 7.3, which is about conservation of momentum. Within this section, we're going to be talking about what happens to our momentum whenever two objects collide with each other. So, when two objects collide, their momentum is said to be conserved, which means that the momentum before and after the collision are the same. So they're equal to each other. So no matter what two objects collide with each other, could be something really big or something really small, the momentum before and after the collision is always the same. That's what we mean by the momentum being conserved. Now, there are two types of collisions. There are elastic collisions, where two objects collide and bounce off each other, and inelastic collisions, where two objects collide and stick together while still moving after impact. Okay, so with my great drawing here, you can see that we have like a large bowling ball hitting a small tennis ball that's just sitting there. So these are going to collide, and so after they collide, we see that they have separated and they're both moving to the right. So let me show you a better example of this. Okay, so this is a simulator for collisions, okay, and I've selected an elastic collision. So this is the big object colliding, and the big object is moving, whereas the little object is just sitting there perfectly still. So let's see what happens. Okay, and see how it bounced right there? That's what tells us it's an elastic collision, okay, because we saw that bounce. Let's see that again. So they collide, and because they bounced off each other, that's what tells us it's an elastic collision. Now, inelastic collisions, that's where upon impact they stick together. So this is usually shown with two carts with magnets. Okay, the magnets are what cause them to basically stick together. In real life, this would be like two cars crashing into each other and basically the bumpers and fenders being stuck together after the impact. Okay, so these two objects, they collide, they're stuck together with the magnets, and now they're both moving afterward, but they're still attached. So let's see an example, a better example of this. Okay, so just like before, we have our large object colliding with our small object. Again, the large object is the only one that's moving. So I've switched this to inelastic collision, so let's see what happens. Okay, so they collide, but see how they're attached to each other? That's what tells us this is an inelastic collision. Let's see that again. Okay, so they hit each other, they're now attached. That is a sign that this is an inelastic collision. Okay, so two types. Basically, if they bounce, okay, that means we have an elastic collision. If they stick together, that means we have an inelastic collision. Okay, so that's pretty easy. Where it gets a little bit tricky is when it comes to our equations. Now, you might think, well, you know, they're colliding. Surely there's just one equation we need to use, but there's not. There's two. Okay, we have an equation for elastic collisions and an equation for inelastic collisions. The good news is they're actually not that bad, but let's go ahead and break down what we have here. Okay, so we have, in these, we only have masses and velocities, okay? So let me label this here for you. Okay, so our mass is always going to be measured in kilograms, and our velocity is going to be measured in meters per second, okay? So use this to try and figure out, you know, how to label our variables. Okay, so then with an elastic collision, we have everything before they collide and everything after they collide. Okay, that's really important. You've got to be able to tell what part of the problem is before and which part of the problem is after. Okay, so on this side it's before the collision, this side it's after the collision. So on this one, you've got two parts afterward, okay, because both objects in an elastic collision, remember, elastic collision, both objects are moving and have bounced off each other. So we have two momentums we got to worry about. Okay, mass 1 times our speed afterward, mass 2 after our speed afterward. Okay, so basically we have two things we have to calculate here. But long story short, two parts here. With an inelastic collision, remember this is where they stick together. Let me show you again. So they go and they stick together moving. Okay, so what we see here is before we have two objects, okay, but only this one is moving. The other guy isn't. Okay, so that's not super important, but basically it means we have two parts. We've got two momentums we have to calculate. But the good thing about inelastic collisions is afterward, we just have one thing to calculate. Okay, this is where, so if we go back to our simulator here, whenever they stick together, okay, we basically treat these as one object, okay, because these are attached to each other. They have one mass, which is going to be here, 3 plus 1, so the mass here is going to be 4, because we add those together, okay, and they're only going to have one velocity, okay? The whole chunk of carts here is moving at 3.8 meters per second. Okay, so on this one, we have one velocity and one object afterward. So the big important thing here is that with elastic collisions, well, first off, with both of these, the first half is the exact same. That never changes. But for elastic collisions, because they bounce and separate, you've got two parts, okay, because they're still separate and moving. But with inelastic collisions, because they have attached to each other, you have one big part that's moving. Okay, so hopefully that helps. I'm not going to go over any example problems yet. That'll make this video too long and crazy, but hopefully this will help you with these equations. So be looking forward to a video where I do a couple example problems that are very similar to what's in our assignment. So that's all I got. Thank you.